All right, share screen, iPad. Mirror. All right, can you guys see the squiggle?
Yes.
Excellent. Okay. Let's see what we'll do today. Okay, folks. So today we're gonna the the plan for today. Excuse me, just gotta move things around a little bit. The plan for today is to to finish up our discussion of thermal conductivity for phonons, and then we're going to start discussing electronic properties of crystals. Electronic properties. That's my favorite part, is electronic properties. Okay, and so let's revisit what we were talking about last time. So last time we were talking about thermal conductivity, and we talked about having a crystal. So we have some crystal where this is, left side is at some temperature and the right side is at another temperature. Then we know that there's heat flux passing through that crystal, and that heat flux is going to be proportional to the gradient, the temperature gradient. It's just 1D, then that in 1D, that's just dt dx. But this is the general way of writing it. And that's the energy flux. That's the temperature gradient. And the gradient and the K, the constant of proportionality, is the thermal conductance or thermal conductivity. Thermal conductivity. And we derived the thermal conductivity last time. I won't go over that derivation again. It's a slightly tricky derivation, I think. Tricky to understand, easy to do, but tricky to understand. The thermal conductivity we derive is 1/3 CVL. So that's a nice simple result that everybody remembers who becomes a solid state physicist. And this C is the specific heat, which is the heat capacity per volume. Shoot, us two. Okay, and the V. Let's see. I need you guys to mute yourselves if you're not asking a question. And so the V is the velocity of the phonons, and the L is the mean free path. And an important thing to understand is that this is the mean free path for Umklaps. Umklap scattering. I'll write it like the Umklap scattering. And so there's sort of, so to understand this, there's sort of two important points to understand if you're going to implement this formula. Two important points to understand. First, you have to understand that that L, the mean free path, is for Umklaps. And these are the big phonons. I like to call them big phonons because they have big K, big wave vector. And the reason for that is because if you have, and I mentioned this last time, but I'll mention it again because I think it's a subtle, sort of a subtle point. If we have the I'm sorry, I'm just being distracted by I'm trying to figure out how I can mute you guys because I'm being distracted by people who haven't muted themselves. It's making it hard for me to give the lecture. I wish that you guys would mute yourself. I'm trying to figure out how to mute you, but I always forget how to do um, all this fancy Zoom trickery. It always seems to be different each time. All right, you guys, I'm just being too distracted by the people who haven't unmuted themselves. So I think I'm just gonna, I don't know. I might just do this lecture on my own without you guys, if you can't unmute yourselves. I mean, if you can't mute yourselves. All right, so it's pretty quiet now. I guess I'll continue. We just wasted several minutes, so I'm going to go over this lecture by several minutes. And so if you guys can't stay, then you can just watch it on the recording. Okay. All right. So um L is for the can you guys hear me? Are you guys still there?
Yeah, we can hear
Yeah.
Okay. Please mute yourself if you're not talking. So L is for the Umklaps, and so what happens is the reason why we have to worry about the big phonons is because if we have two phonons that are scattering, like K1 plus K2 goes into K3, then it only really matters if we have to cross that Brillouin zone boundary. So if that's K1, K2, then, and this is then K3, then it's really important that we cross that Brillouin zone boundary, because then I can draw a reciprocal lattice vector like that. That's G. And then this is the K3 is actually pointing in the other direction. And so that reverses direction. And so that's how and that's important because that's how we get the energy to reverse direction. And so that's how we relax the non-equilibrium distribution. So because it's a subtle point, and I won't try to stress it too much, but the point is that for thermal conductance, it's a non-equilibrium system. One side is hotter than the other. And so we have a non-equilibrium distribution of phonons, like we have more going in one direction than in the other. It's not all in equilibrium. And so the processes that cause impedance to the flow of heat are the processes that relax the non-equilibrium distribution of phonons. And so those processes are the ones that reverse the phonon direction. So that's critical. But the only ones that can really do that is the Umklapp scattering. Okay, so that's an important point. It's kind of subtle, but it's important. And so that means that we want K then to be bigger than, say, half the Brillouin zone boundary, which means then using a simple model, we'll just say that K has to be bigger than half the Debye wavelength. And so that means that we only care about phonons whose frequency is on the order of half the Debye frequency. So that's the reasoning, because if the phonons are bigger than half, then if I add two of them, they're going to cross the Brillouin zone boundary and umklapp. That's the concept. Okay, so that's the one really important one. So these are the important ones. We only care about the big phonons, the big ones. And then the second important point is that the mean free path, if L is the mean free path of phonons, then the mean free path goes as 1 over the density of phonons. And that's sort of, there's a simple geometrical argument for that. You can just kind of see it. Like if I have a crystal and if I have very few phonons, like those dots are phonons. So now I'm thinking of the phonons as like sort of localized objects. You can think of them as wave packets. So if I have very few phonons, then the distance between them is big, L. And the distance between the phonons is kind of like the mean free path. So it's intuitive, I think, that the if the phonons are further apart, then the chances of them, the distance they can travel before hitting each other is bigger. So the mean free path is bigger. So I would say low density, low density of phonons, then I have a big mean free path. But on the other hand, if I have a high density of phonons, high density, you see lots of them, then the distance between them is going to be small. So that's L. And so then we're going to have a small mean free path. So you can kind of, there's better ways to make that argument, but that's the basic argument. And so L goes as, is kind of like the distance between the big phonons. So I just need to know what is the, which goes as 1 over the density of the big phonons. All right. So then, okay, so that once you understand that, then understanding thermal conductivity is pretty easy, because then for the temperature dependence of the thermal conductivity, then we need, we see that K is equal to 1/3 CVL. And so then the question is, which term dominates? All right. And so there's, and that's the one that determines the temperature dependence. And so if we have, so there's 3 important regimes. And those regimes are the temperature much less than the theta Debye, temperature on the order of the theta Debye, or maybe a little less, or on the order, and then temperature much bigger than the theta Debye. And so the question is, which of these 3 terms dominates in the temperature dependence in those 3 regions? And it turns out that in this regime, it's the mean free path that dominates. In this regime, it's the mean free path, but in this regime, it's the heat capacity. And I'll explain why for each of those. So let's consider this regime, which is the one I did this last time, but I'll just sort of remind you the result. If we're like on the order of the theta Debye, then we ask ourselves, then let's take a look at the mean free path in this temperature regime. So the mean free path is going to go like 1 over the density of the big phonons who have frequency on the order of 1/2 the Debye frequency, and that density is going to go as the occupation number for a phonon with 1/2 omega Debye, where that's the Bose-Einstein distribution function. Bose-Einstein distribution function. So because the density of phonons is going to be proportional to the number of phonons, the number of phonons per volume, and the number of phonons in a particular mode is the Bose-Einstein distribution function. So the density of phonons will go as the Bose-Einstein distribution function for those big ones, which is e to the energy 1/2 h bar omega Debye over kt minus 1. And if we think of h bar, if 1/2 h bar omega Debye is bigger than kt, then we can just ignore this part. So we'll ignore that. And so then we see that we have 1 over n phonons goes as, I just invert that formula, e to the 1/2 h bar omega Debye over kt, which is equal to e to the theta Debye over 2t, since theta Debye is equal to h bar omega Debye over k. Okay, and so we see that L, the mean free path. So now we see that L, the mean free path, goes as e to the theta Debye over 2t, and that's exponential. And so exponential terms dominate. You guys have seen that before. If I have some expression, if there's an exponential term, that typically dominates. And so that's why the mean free path dominates in this temperature regime, because the other terms, the velocity of a phonon is not strongly temperature dependent, and the heat capacity, we derived that the other day, it's not exponential. And so it's so this dominates. And so that's why if we write the thermal conductance, then if it's a function of temperature, then in the regime of the Debye temperature, it's going to look like this. It's going to be exponential. It's going to, the thermal conductance is going to go like e to the theta Debye over 2t. That'll be the dominant temperature dependence. But now let's look at these other two regimes, because we have this other regime. We have the T. Let's look at this high temperature regime. T much. I'm sorry, did I write these incorrectly? Shoot. I'm sorry, I made a mistake here at the very beginning. This was T bigger than theta Debye. I'm going to erase this. And here, this was T smaller than theta Debye. So okay, so now let's look at the temperature bigger than theta Debye. And for temperature much bigger than theta Debye, the high temperature regime, then what we see is that we then just do the same argument. We have L is proportional to 1 over the density of phonons, and the density of phonons goes as the Bose-Einstein distribution function for the big phonons, h bar omega Debye, which equals 1 over e to the h bar omega Debye 1/2 over kt minus 1. But now it's a different regime, because now I have kt is much bigger than h bar omega Debye. And so then I have e to the 1/2 h bar omega Debye over kt is approximately equal to 1 plus, I just do the simple expansion, the Taylor expansion of the exponential to the first term. And I plug that into there. And so I see that the density of phonons now goes as h bar omega Debye. It's going to go as kt over 1/2 h bar omega Debye. And so then we see, then what we see then is that then we see then that the mean free path is going to go as the inverse of that, which is 1/2 h bar omega Debye over kt, which is proportional to 1 over temperature. So the important thing is here is that we see that the density of phonons This is sort of a famous result. The density of phonons is proportional to temperature. So at high temperatures, as you increase the temperature, you just get more and more phonons. The density of phonons is linear in temperature as I get hotter and hotter. And so that means that the mean free path goes as 1 over temperature for phonons, for big phonons, the ones that matter. And so then we see that the thermal conductance, thermal conductivity. So here I have theta debye. So here it's exponential, and then it kind of slows down a little bit. So it's exponential kT over there. And then as I go down in temperature, it goes as 1 over temperature in this higher temperature regime. And then then the last regime is the low temperature regime. And in the low temperature regime, you look at this term, K equals 1/3 CVL, and you notice that that at low temperature, then L gets big. And it gets so big that L becomes on the size of the crystal, size of crystal. And so if I reduce the temperature and the mean free path hits the size of the crystal, what does the mean free path do as I keep reducing temperature? What is the temperature dependence of the mean free path as I keep reducing temperature? Can someone tell me?
It gets bigger.
Well, it did get bigger. It got bigger and bigger, and then it hit the size of the crystal. So now at some temperature, I'll call it T prime, the mean free path hit the size of the crystal. And now I keep going down in temperature. What happens to the mean free path?
Does it stay the same? Maybe.
Yeah, exactly. It has to, because the mean free path is going to be the size of the crystal. So that is the mean free path, because the phonon will move until it hits the edge of the crystal, then it will bounce, right? So the mean free path is the size of the crystal. So it'll be temperature independent. Then L has no temperature dependence. And so then so you see that at low temperature, the mean free path is no longer important. It no longer dominates the temperature dependence. It's just a constant. The velocity is also a constant. And so what determines the temperature dependence of the thermal conductance, thermal conductivity at low temperature? Tell me, someone.
The specific heat capacity?
Exactly. The heat capacity. Exactly. And so what then is the temperature dependence of the thermal conductivity at very low temperature, where very low means temperature much less than theta debye? What is it? Tell me. For a three-dimensional crystal,
T cubed.
Perfect. That's exactly right. We derived it the other day. So we see then that K, that's L. So we see that K then is proportional to the heat capacity, which has a temperature dependence, and that dependence is proportional to T cubed. So then what we see then is that I'm going to go back to the picture above, and you can see then that at low temperature, the heat capacity goes as T cubed. And so that's T cubed right there. I didn't draw it very well. It's a pretty crappy drawing. But you see, and so that means that the thermal conductance turns over. So there's a hump, there's a bump. So the thermal conductance is rising because that mean free path is getting longer and longer and longer, so fast, exponentially. But then boom, it hits the edge of the crystal, and then the thermal conductance gets smaller because now the heat capacity is getting smaller and smaller. So that's how it works. And so this then is the dependence of the heat capacity. And that's what you really see in real life. You know, I could even draw like a actual data. I mean, so if I look at the thermal conductance in watts per centimeter Kelvin, then here at 10, 100, I'm going to get something that looks like this. boom, bup, 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 boom, boom. And so this is going to be 10 Kelvin, and this is going to be theta debye, and this is going to be 100 Kelvin. And that's the thermal conductance, thermal conductivity for sodium fluoride crystal dominated by phonons, where the theta debye is equal to 50 Kelvin. And this is a log plot. So this is so that's T cubed here and exponential there and 1 over T here. Okay, so that's actual data. All right, so those simple arguments actually explain the real world. Okay, so now we're going to move to the next topic. So now it's time for us to switch gears and do the next topic, which is electronic properties of crystals. Okay, so now we're switching gears. We're going to discuss electronic properties. So now we've talked about electrons already in this class, but not too much. We only talked about electrons in terms of bonding and how they provide the glue that holds together crystals. We talked about that, covalent bonding, ionic bonding. Remember, we talked about that very early on. But now we're going to talk about electrons, because electrons can do more than just hold a crystal together. The electrons can move around in a crystal and conduct. So electrons can, move around, jump around. They move around, they jump around, and they conduct electricity, and they absorb light, and they carry heat. So we'll talk about all of these things, because those are the things we need to understand crystals. That's like basically the property of materials around you. So okay, and so for example, if we want to answer, like, here's a question. I have a piece of glass and I have a piece of copper. And then we can ask ourselves, I mean, you guys know that they're different, right? I mean, glass is transparent. It doesn't conduct heat very well. It doesn't conduct electricity, whereas copper is opaque. You can't see through it. It's ductile. It conducts heat really well. It conducts electricity really well. They're totally different. Why? And that's the question. Why are they different? Why are these two materials so insanely different? You can't make a window out of a piece of copper, right? So, okay, that's what we're trying to answer. And the reason is because of the electrons. It's because what the electrons are doing in these two materials. And so that's the goal of what we're doing now in this course, is to try to figure out why is glass different from copper. All right. And so the simplest theory of electrons in a material is the Drude model. Simplest theory is the Drude model. And that was around 1900. And it's a very successful model. It's very good. It works really good. It actually was very good for looking at high frequency properties of materials. And so the idea is that the idea of the Drude model is that I have the atoms, and I have the and I have the cores. So these are the atom cores. And the cores are stationary, but the valence electrons are free to move. And let me explain what I mean by that. Like, let's take a look at copper. If I look at a copper atom, then the core is basically all the filled levels. And the filled levels are the 1s2 level is filled all the way up to the 3d10. All right. The 3D level has 10 electrons in it. It's all filled up. And so this filled shell is the core. But then I have the valence electrons. Does anybody remember what's the valence electron configuration for copper? Somebody tell me. Anybody know? I'll give you a hint. It's just one electron. It's in what shell? Do you guys know? Chemistry question.
4s.
Good. Very good. Yeah. 4s1. The one means there's one electron in the 4s shell. That's right. So this then for copper is the valence electron. So when I draw these cores, I mean, I'm drawing this little circle with the plus inside is the core. But the valence electrons are free and they just bounce around like a gas. Okay. So it's a gas. So valence electrons form a gas of electrons. And I should say a classical gas, because that's all they knew back then was classical physics. So they say, oh, there's just a classical gas of electrons, just like in, chemistry. And those electrons scatter off the cores. So the gas, they go boing, and they bounce off the cores. All right. So, boom, there's a core, and then they go boink and they bounce off. And so this model works very well. And I'm not going to go into it too much because we're not going to focus on the Druid model that much. It is useful for a lot of things, high frequency especially, but I'm not going to get into it too much now. We'll maybe do a little bit of it later in the course. But the point I want to make is it gets a lot of stuff wrong. So let's focus on the failure. Let's see the glass as half empty, not half full. And so there's a lot of failures to this model. And let's talk about the failures. So one failure is that people noticed that electrons in crystals have a very long mean free path. L can be very long. For example, you can have people observe mean free paths on the order of a millimeter. That's really gigantic. And the distance between ion cores. Can anyone tell me what's the distance between the ion cores in a crystal? Anybody remember?
Like
10 to the
3
minus 10
angstroms.
meters.
Exactly, 3 angstroms. That's a good number, about 3 angstroms. Sometimes it could be, 1.5, 2, 3.5, I don't know, whatever, but it's like around 3. 3 is a good number. So the interatomic spacing in a crystal is on the order of 3 angstroms. So there's a pretty big difference between 3 angstroms and a millimeter. I mean, geez, many, many orders of magnitude, because, one micron equals 10,000 angstroms. And so a millimeter is 1,000. Okay, so there's a factor of 10 million difference. So that's quite a change, so you would expect, using the Druid model, you would expect the mean free path to be on the order of angstroms, because there's so many of those ion cores. The electron's surely going to hit one pretty soon. So this is a crazy difference. Like, we're talking like an 8 order of magnitude discrepancy. So like, oops, that's a fairly big discrepancy. So that's a big failure. Next failure is the specific heat. The specific heat is, classically, the Druid model got it completely wrong. Because classically, we know the specific heat. We actually derived it in class. The specific heat for a classical gas, it's like, totally trivial to derive. The specific heat is du, dt, and the u, the classical u for a for a gas is 3/2 nkt. All right, that's the u for a gas, classical gas. And so you take the derivative of that and you get 3/2 nk. So that's the heat capacity. That's what you should get. All right, that should be the heat capacity of the valence electrons, 3/2 times n, where n is the number of electrons. But that's totally wrong, because when they measured it experimentally, they found that this is less than, when they measured experimentally, they found that the experimental one this was like less than the experimental one divided by 100. So the experimental heat capacity is like 100 times 3/2 nk, n times k. So and it's even bigger than that often. So it missed 2 orders of magnitude. All right. So the heat capacity that you measure in crystals is gigantic, 100 times bigger than what you would expect classically. So like, wow, that's a gigantic failure. And then another question is this question: why are some materials insulators and some are conductors? Some crystals are insulators and some are metals. So why do we have a metal, and why, on the other hand, do we sometimes have an insulator? Because if I have a material and I have a bunch of valence electrons, then if they're swimming around, then I should always get electrical conductions. Every material should be a metal. Almost every material, any material that has some free valence electrons should be a metal. So the Drude model totally blows it. It gets that wrong. So it doesn't explain that. Okay, so those are some pretty big failures. And so to answer the reason the Drude model got that wrong, the reason it failed, is because it did not take into account something very, very important. Can you tell me what that something is? Somebody tell me.
Quantum mechanics.
Very good. It didn't take quantum mechanics. It missed quantum mechanics. So to fix it, quantum mechanics. All right. So now let's use quantum mechanics. And so let's now do a quantum mechanical treatment of the electrons. And that answers all those questions and fixes everything. All right. That's the bottom line. But we're going to step through it. That's the point of this class. This class is to step through the reasoning so that we can understand how quantum mechanics answers all those questions. So let's consider the simplest quantum mechanical model of electrons in a crystal. We're going to do a simple one, then we're going to do a harder one later, but we'll start with the simple one. And the simple one works pretty well. The simplest one is what we call the simplest quantum mechanical model, which works pretty well. So it's worth learning, but it doesn't get band structure right, but it gets a lot of other stuff right. The simplest quantum mechanical model we call the free electron model. Free electron model. And it was made in 1933 by Sommerfeld and Bethe. So that was pretty big feather in their cap, I'd say. I wish I came up with it. Okay, and so so the big idea that they had is, and it's like so simple and trivial and yet so important. Their idea is that a crystal is equal to a box of electrons, the valence electrons. But what we do is we ignore the cores, and we ignore the electron-electron interactions. the Coulomb repulsion between the electrons. We just ignored it. And so, you know, that's like why physicists love to make really gross approximations, because because in the past, really famous physicists made really gross approximations, which really worked really well. And so that's the culture they determined the culture of physics. We love to make gross approximations because they sometimes work really well. So there it is. So that's a crystal, and the electrons are just free to move in the crystal, the valence electrons, and there's no interactions. There's nothing stopping them. They're just free to move. And so you'd say, well, that's a gas, right? Free to move. So it's like a gas, but and there's no cores. You just ignore them. Just say, they're not there. Just pretend they're not there. And then, but the reason why this is not a classical gas is because they take quantum mechanics into consideration. They're free to move, but we must use quantum mechanics. And for quantum mechanics, then what we have is the most famous quantum mechanics problem, which is particle in a box. Particle in a box. So we got to use the particle in a box model of quantum mechanics. Okay. And so then what that means then is we think of it like this. So this is the picture that we have, is that the crystal is like this. So we have a box. So this is a box in quantum mechanics where this axis is energy, and this axis I'll call X. So that's a box. That's a potential box in quantum mechanics that you guys have all learned in quantum mechanics. And so we have the electrons filled up to some highest level in the box. So these are all the electron states, filled states. And the highest filled state, we're just going to give it a name. We're going to call it the Fermi level. And so that's the picture. And then this, we're going to call this V equals 0 is the vacuum level. All right. And so this then, and this energy is very famous. What do we call that? Somebody tell me.
Work function.
Exactly. That's the work function. So these filled states, so these electrons occupy a particle in a box states up to EF. All right. So that's the quantum mechanical picture of electrons in a box. They're just filling up those states. So now let's work through the details of those states. Okay. So now let's calculate those states. So now we're going to do some quantum mechanics. Let's calculate those states. So this is sort of just review because you guys all have done that. You all have done this. So let's use quantum mechanics for the particle in a box. And so what we're going to do then is we're going to have a box. And the box is going to be of length L. And let's do it in 1D first, and then we'll do 3D later. Let's first do 1D. And so this is X equals 0, X equals L. And so we have the Schrodinger equation, the Hamiltonian is just kinetic energy, negative h bar squared over 2m del squared, because there's no potential, because it's free. The electrons are free to move around. They don't hit anything. So it's just kinetic energy in the Hamiltonian. And so then we have to solve H psi equals E psi. That's the Schrodinger equation to get the eigenstates. And so we solve it, and then we get that psi is equal to what? Somebody tell me, what's the eigenstate?
Root 2 over L sine n pi x over L.
Yes, that's right. That's good. That's the particle in a box. Exactly. but there's a nuance. And so, and I didn't mention this, but I should have. There's a nuance, which is that it turns out that there's different ways for us to define the boundary conditions. So the eigenstate that you just mentioned is the eigenstate for a hard wall, and you're absolutely right. You know, that's correct. But it turns out that in solid state physics, it's more convenient to use a different set of boundary conditions, which is called periodic boundary conditions. And we did that periodic boundary conditions already for the phonons. So you guys, you know, have heard of it. And so, this is ever so slightly different maybe than what you did in quantum mechanics, but for solid state physics, it's convenient to use periodic boundary conditions. And so what that means is we take the crystal and we take one end and we bring it over so that the two ends touch. So we go from a bar to an annulus. Okay. And
So does that mean our states are just going to behave as free particles then?
yes, exactly. And so that means that psi of 0 has to equal psi of L. And there would be free particles. So now what's the eigenstate?
It'd just be a prime wave.
That's exactly right. So now the eigenstate is going to be 1 over square root of L e to the I kx. And you might be thinking to yourself, wow, that's pretty different. Like a plane wave is different from the sine function. And it is, you know, a plane wave is a traveling wave, whereas the sine function is a standing wave. They're quite different. And so you think, wow, that must mean like I'm going to get different physics if I like have a bar versus an annulus. And the answer is no, you don't. You could do all of solid state physics using sine waves instead of plane waves. It's just inconvenient. It's just a big pain in the ass, so we don't do it. It doesn't, but the physics doesn't change. You know, that's like a different basis set. You know, you can use different bases in quantum mechanics. So this is just, it doesn't change the physics. The boundary conditions don't change the physics. So don't get caught up in that. Change the physics. So just embrace periodic boundary conditions and don't worry about it. Just smile and be happy. Okay, and so that's the eigenstate then, are these free waves. And they're just waves traveling along, happy little waves. And so, and I also want to point out to you, well, I'll ask you a question. So this is a wave with plus K, but I could also have the wave going in the other direction. Wow, that was a lousy wave I drew, minus K. And I will ask you, so that's this one, but this one is psi of x equals 1 over square root of L e to the minus ikx, right? And so I will ask you a question. Are those two states different? Are they really just the same eigenstate, or are they two different orthogonal states? Can someone answer that question? Just try. You don't need to spend a lot of time. Either you know it or you don't. Just blurt out an answer. What do you think?
They are different.
That's exactly right. Because if you integrate them, psi star psi, you know, psi 1 star, psi 2 integrated over L, they would go to 0. That's right, because it would be a periodic function. So that's right. They're orthogonal. So these are orthogonal states. And that's important because when we count the modes, we're only counting all the orthogonal states, you know, all the orthonormal basis states. And so when we're counting modes, so when I count modes, the negative modes, the negative going electron waves are different than the right going electron waves. Those are completely different states. Okay, so that's nice. All right, and so then let's notice then that from the periodic boundary conditions, then we have psi of 0 equals psi of L. And so that means that e to the I 0 is equal to e to the I KL. And so that means then that KL equals what? Tell me.
Q pi n.
Exactly. 2 pi n. And so that means that K is equal to 2 pi over L times n. And that's pretty cool because that means that K is quantized. K is quantized. Oh my God. And that's a little bit weird and freaky because you might not be used to it, but you should be used to it because it is exactly what we got for the phonons. So I want you to see that the K, the momentum, is quantized due to the size of the crystal, L. And that's the exact same quantization that you got for the phonons. So the quantization of K is really simple. It's the same for electrons. It's the same for phonons. The K is easy. It's the energy that's hard. All right. And this quantization of the K, it's just this trivial argument. You know, I have a guitar string 0 to L, and I can add like an integral number of wavelengths. And so if L is an integral number of wavelengths, then lambda is equal to L over N. And that gives you this quantization condition. So it's trivial. You've seen it a million times. Now you're seeing it again. Okay. So K is quantized just like before. And then we get energy. So now let's do energy. And so if K is quantized, then energy is quantized. And so the energy, En, is just going to be equal to h bar squared, K squared over 2m. All right. You know, that's just the kinetic energy, P squared over 2m. That's what you get when you solve the Schrodinger equation. I'm not going to go through the details because you guys have all done it 100 times. And if you don't remember, go back and, you know, look in a book or ask me in the TA, you know, in office hours, if this is unfamiliar to you, because this is really important. And so then I can just say that the energy will be h bar squared over 2m times K squared, where K is going to be 2 pi over Ln. And so then you get this famous relationship, you know, that the energy is 2 times h bar squared pi squared n squared over m L squared. All right. And so this is then the energy levels in my crystal. So I'll just draw it like this. So then we get all these energy levels. N equals 0, N equals 1, 2, 3, 4. We get all those. And then we can put, how many electrons can we put into each energy level? How many? Exactly. So Pauli exclusion principle says 1 electron per state. And so 2 electrons can per level, since we have spin up and we have spin down. Okay, so the Pauli exclusion principle is actually sort of a fancy thing, and you learn it in physics 137b. So some of you, I guess, are learning it now, and it says that the many-body wave function of any system of fermions has to be antisymmetric under particle exchange. So it's kind of subtle and sophisticated. It's a very beautiful, weird thing. And if you look at that properties of the antisymmetric wave function, then one of the consequences is that I can only have 1 electron per state. But the state is defined not just by the orbital level, but also by the spin of the electron. So each orbital level with spin is 1 state. So for each orbital level, then there's 2 states. I could have spin up or spin down. So the consequence then is actually pretty simple. It's just 2 electrons per state. So I'll draw them like little arrows. So n equals 0, I have 2 electrons. N equals 1, I have 2 electrons, 2 electrons, 2 electrons. So I'm just filling them up and up and up and up to the Fermi level. Okay, and so that's it. That's the quantum mechanical picture of a crystal. That's the free electron model. We just did it basically. That's the whole thing. But there's always details, and so let's do some more details. So let's consider. So there's many details. Like for example, let's consider counting the states is very important. Counting states, because if I'm in 1D and I start counting states, then we just did it. You do that. You just are looking at the number of waves on a string. And then we see that from periodic boundary conditions, we're going to get the Ks, they look like this. If I was to draw them, on an axis K, and the distance between them is going to be 2 pi over L. And that should be very familiar from the phonon picture. All right. So then, but now, and I can see then that the eigenstate in one dimension for an electron is going to look like 1 over square root of L E to the I K N X, where these are my KNs up there, spaced by 2 pi over L. Now let's look in 2 dimensions though. So now let's go to 2 dimensions. And in 2 dimensions, periodic boundary conditions tells me that I have to have an integral number of waves in both directions. So that's my periodic boundary condition. It means I have an integral number of waves in both directions. And so that means then that my Ks are going to be quantized in 2 dimensions. So I have a grid of Ks in 2 dimensions. So, and you can see that in the X direction, the distance between them will be 2 pi over Lx, but in the Y direction, the distance between them will be 2 pi over, you guessed it, Ly, where this is Lx and this is Ly. Okay, so that's my K, that's my allowed K states. Just a simple generalization of the one-dimensional case. But now we write the but every one of those dots represents a state, a quantum mechanical state. So now we can write the eigenstates like this in 2 dimensions. So the eigenstates are going to be psi n. Now it's going to be the eigenstate is going to be a function of x and y, and so I'm going to have, this is sort of a simple way to do it. You can just take the x eigenstate and the y eigenstate and just multiply them together. So I have 1 over square root of Lx times e to the I k n x times x times 1 over square root of Ly times e to the I k n y y, and that's going to equal 1 over the square root of the area of the of the 2-dimensional crystal times e to the I k n x plus k n y y. All right, which I can write as 1 over square root of a e to the I. People don't really do all this knx, kny stuff. They just will do k vector dot r vector. That's the more compact notation that everybody likes. And so then we can then generalize this to 3 dimensions. And so we see now that the electronic eigenstates in the 3-dimensional crystal are gonna look like, you just do a simple generalization of this concept, and now you can see that I can write them as 1 over the square root of the volume of the crystal times, well, let's just write them in the compact notation, k dot r, where e to the I k dot r is now understood to be e to the I k n x x plus k n y y plus k n z z, where now we see that the k's like the so the k vector in 3 dimensions is going to be a quantized object, is going to be for the nth state is going to be 2 pi over lx nx, oops, nx comma 2 pi over ly ny 2 pi over lz nz. So when I say n, I'm really referring to 3 numbers, nx, ny, nz. So it's sort of like there's 3 quantum numbers to the eigenstate, nx, ny, nz. And so then you can see that the allowed states live on a grid, live on a 3-dimensional grid in K-space. And we've already talked about this for phonons, so these concepts should be somewhat familiar. We can just draw it. So that's, I could call that Kx, Ky, Kz, and so there's a 3-dimensional grid. And I have trouble drawing 3-dimensional grids, but you know, something like that. Okay. And so if I wanted to say, let's consider states with same energy, and let's define the energy as equal to h bar squared k squared over 2m. Remember, that's just p squared over 2m, where p equals h bar k, just reminding you all these little quantum mechanics formulas. So if I want to look at the set of all states that have the same energy, what does that set look like? Tell me.
A shell.
Yeah, exactly. It's just a shell, a spherical shell. Oops. Spherical shell. States with same energy live on surface of sphere. That's right. Good. So that's the picture you should have in your mind. And so what we can do then is there's this important thing. Now, remember, there's this important thing where let's talk about now the Fermi energy. Because I told you that, you know, a metal is a box of electrons filled up to the Fermi energy. That's the box filled up to the Fermi energy. And so let's ask ourselves, what is the Fermi energy? So suppose we're given the volume of the crystal and we're given n is the number of electrons, then what is the Fermi energy? All right. And so that's the question that we want to answer now. So I have a crystal, I know the size, I know the number of electrons. What's the Fermi energy? So that's a reasonable question to ask. And so let's derive it. It's really easy to derive. So here's the way to think about it. Let's consider K-space. So go to K-space. And in K-space, you can see that this picture, where here I'm drawing, this is in energy versus X, but this picture converts to this picture where now I have this funky grid where this is Kx, Ky, Kz, and I have this grid. And now I have a sphere. And this sphere is filled up to some maximum wave vector, Kf. But you see that if I define EF equals h bar squared KF squared over 2m, then what is the relationship between this sphere that I drew here and these electrons that I drew up above? Can somebody tell me? Tell me the relationship. Maybe I'll make my question more specific. Consider all the electrons in this thing that I drew. Okay, all the electrons in a metal. There they all are. Where are those electrons in K space relative to the sphere that I just drew in the
They should be at the borders on the shell, so they should all have the Fermi energy.
Well, I want to, but look, I want to talk about all the electrons. So all these, so these ones too. I'm talking about all of these electrons. All right, every goddamn electron in the metal. So where are all those electrons relative to this sphere that I just drew in K space? All the electrons.
They're all within the sphere.
Exactly. That's the key concept. And so you all must understand that. So the electrons in a metal live in the sphere. Now, the sphere has a radius, which is the Fermi wavevector. Did I write that down? It's at KF, and the energy is the Fermi energy. And so this sphere has a name. It's the blank sphere. What do you think it's called?
Fermi sphere.
Fermi sphere.
Very good.
Very
Very
good.
good.
Very good.
Yeah. Now mute yourself. Okay. All right. So that's right. They live in the Fermi sphere. Fermi. He got his name on everything. He pissed on everything. That's the Fermi sphere. And this is the Fermi wave vector. And that is the Fermi energy. Oh my God. Okay. All right. Fermi. Okay. And so let's use this concept of the Fermi sphere to figure out the Fermi energy. And it's really, there's a really cute little argument, which is that to find the Fermi energy, what we can say is that if I consider the Fermi sphere has a volume, which is the volume of a sphere is 4/3 pi kf cubed. All right, that's the volume of the Fermi sphere. Volume of Fermi sphere, which contains all the electrons of the metal. And so if I can ask myself, how many little K points are in that sphere? Because remember, that's a sphere that's living in the grid, the three-dimensional grid of K space. And so the number of points, to get the number of points, I have to multiply this times a quantity. Can you guess what I have to multiply it by? Can anyone guess? Well, I'll just tell you.
Density?
Exactly. The density of states. That's right. Exactly. That's the density of states. Density of states in K space. And we've talked about this already. Especially like, remember when we were doing the Druid model? This is exactly the same as the Druid model. So density of states times that's Fermi sphere. Now, that tells me all the K states living inside of the Fermi sphere. How many are there? What's the number?
N.
Yes, N, the number of electrons. That's right, because the electrons go in to the states and it's the same thing. Like all those, that's all the states occupying electrons. So the number of states is equal to the number of electrons. That's exactly right. It's equal to N, except there's one little nuance. It's not exactly N. It's going to be what? It's almost N.
2n.
Ah, that was a really good guess. That was a really
N
good
over
guess.
2.
Ah, n over 2. That's right. N over 2. Because each of those K states can take 2 electrons. So there's only going to be n over 2 of them. Okay. So that's the trick. And so now we ask ourselves, what is the density of states in K space? So this is the 3-dimensional density of states, DOS. And the density of states in K space is what? I'll give you a hint. Remember back here to this 1-dimensional picture, we have one state per delta K is equal to 1 over the number of states per delta K is 1 over 2 pi over L is equal to L over 2 pi. And so that's the density of states in K space is 1 state per delta K, L over 2 pi in 1 dimension, right? Okay, so we've done this before. So now I'm asking you, what's the density of states in 3 dimensions? What's the density of states in K space for 3D? Tell me.
L over 2 pi cubed.
Exactly. Perfect. And so now let's plug it into this little formula that we just did, and we have L over 2 pi cubed, plugging into that formula, times 4/3 pi kf cubed equals n over 2. And solve that like in one line of algebra, then you can solve that and get that the Fermi wave vector is equal to 3 pi squared n over volume, which is L cubed, to the 1/3 power. And that's it. We got it. That's the Fermi wave vector. And then the Fermi energy is just going to be h bar squared kf squared over 2m. So I just plug that into that, and I'm going to get that the Fermi wave vector is equal to h bar squared over 2m times 3 pi n to the 2/3, where n is equal to n over v equals density of electrons. Density of electrons. And it's the density that matters, because this K Fermi, if I write it in terms of density, is going to be 3 pi squared n to the 1/3. Okay. So so I got the Fermi wave vector and the Fermi energy. And of course I could always define the Fermi velocity. Fermi velocity is just equal to momentum over m. It's just a very trivial relationship, which is going to be h bar kf over m, which is just going to be well, I'm not going to write it out. You just plug that kf in. That's what it is. That's the Fermi velocity. And I can also define the Fermi temperature. Man, he got a lot of things named after him. Fermi temperature, which is just going to be the Fermi energy in terms of degrees, just divided by the Boltzmann constant. Okay, so these are all important things. And so for a typical metal, then we have N is on the order of 10 to the 22 electrons per centimeter cubed. That's typical. And so this leads to a Fermi velocity, very typical Fermi energy is on the order of, can somebody tell me? Do you know? Does anybody know? Guess. Just guess. Don't be so shy.
Uh, 2 billion electron volts.
Good. Thank you for guessing. Thank you for trying. No, that's GeVs. And so those are the energies that you get like at CERN when you do collision experiments. And that's a good guess because there certainly are billions and billions. So you might think that it could go that high, but it doesn't go that high. I will just say in solid state physics, the typical energy scale for all of our processes is on the order of an electron volt. Sometimes it's milli electron volts, sometimes it's hundredths of an electron volt, sometimes it's 10 electron volts, but it's the electron volt that we care about. So in solid state physics, it's the electron volt. So if I ever ask you what's the energy of anything, can you guess? What you should guess is an electron volt. Okay. So in solid state physics, if someone says, what's the energy, say an electron volt. Now, if you're in a high energy class and someone says, what do you think the energy is? Then you would say a megavolt. If it's nuclear physics, a megavolt or a gigavolt. But in solid state physics, the answer is always an electron volt. All right. Okay. And so the Fermi energy is, you guessed it, it's an electron volt. And so 1 electron volt, but let's just say, but maybe two electron volts is pretty typical. It's a couple of electron volts. And so then that then leads us to a typical Fermi. So if the Fermi energy is around 2 electron volts, then what's the Fermi temperature? What's the temperature that we would associate with that energy? Now I'm just asking you to convert 2 electron volts into Kelvin. And can you guys do it? Somebody do that. What's an electron volt in Kelvin? This is actually an important conversion. You should know for solid state physics, it's important to be able to convert between electron volts and Kelvin. So what's 2 electron volts in Kelvin? Somebody tell me.
20?
Yeah, 20,000 though. So that was almost right. 20,000. Okay, so that's good. It's 20,000 because there's 10,000 degrees per electron volt. So an electron volt is a really high temperature. Okay, so if a particle had an electron volt of energy, if I have a gas of particles and every particle has an electron volt of energy, the gas is at 10,000 degrees. Okay, so it's really hot. So that's a trip. When you think about it, and the velocity, if you work it all out, the Fermi velocity is on the order of 10 to the 8 centimeters per second, which is pretty fast, but not as fast as the speed of light, because that's, the speed of light is like 10 to the 10 centimeters per second. So VF is on the order of 1/100th of the speed of light. Okay, so the electrons at the Fermi energy are moving like 1/100th the speed of light, pretty fast, but not that fast, compared to like a high energy experiment. So it depends on your definition of fast. Okay, so that's just giving you some numbers and orders of magnitude. And so now you have this picture in your mind of what is a metal. Because now if I give you a metal, I say, here's copper. How does a solid state physicist think of copper? And so this is how you think of it now. This is a metal. A metal, to think of this metal, we think of it in K space. I have KX, KY, KZ, and I have this grid of all the possible states. I have a crystal, like a crystal of copper, and has some size. And so that size determines the size of the grid in K space. And so I have this grid in K space. And in that K space, I have a sphere. And that sphere is filled up. Those are all the states that are filled up. That sphere has a radius called the Fermi wavevector. And this is just filled up with electrons. So that's the Fermi sphere. And it's filled with electrons. So that's a picture you should have in your mind. Like you should visualize it like that's a metal. It's the Fermi sphere. All those electrons living in those states in K space. That's the metal. Okay. And now at T equals 0, this is the picture at T equals 0, meaning that no temperature. Now let's turn on temperature, KT. So what happens at KT? Now let's turn on T not equal to 0. I still have that Fermi sphere. It's there. But what happens now? So now I can give the particles like energy on the order of KT. So now now I turn on temperature. In other words, I take my piece of copper, which was really cold at T equals 0, and I attach it to the surface of the earth. I drop it onto the floor. Okay. I take it on my doer and I drop it onto the floor. Now it comes to thermal equilibrium with the earth, which is room temperature, KT. What does that do to my Fermi sphere? Can somebody tell me? Guess.
Are some states outside of this sphere populated?
That's exactly right. That's exactly right. Because a simple way of thinking about temperature is that temperature means that I can just give KT of energy to all the particles, because that's what temperature is. It just means all the particles have like KT of energy. That's what it means to be at temperature T. So that means I can give those particles like KT of energy. And that means that that an electron inside of the sphere can now be excited outside of the sphere. So it leaves behind a bubble, a hole. So I can call that a hole. And so I get these little bubbles. And then I get little electrons populated outside of the Fermi sphere. So you can see that I'm getting little bubbles. It's getting frothy, like, I don't know, boba tea or something. It's like little bubbles. It's not exactly boba tea. Okay, it's getting frothy. But what about the electrons inside? Can they get out? Yes or no? Deep inside.
No.
Why not? Why not? That's the right answer. They can't get out, but why not?
The energy difference to the surface is greater than KT.
That's right. And why can't they just be excited inside of the sphere? Why can't I just go from one state to another state inside of the sphere? Why can't I do that?
Because those states are probably already occupied.
Exactly. The states are already occupied and electrons are fermions. So you can't move electrons inside of the sphere. They don't move. They can't move. So can't move deep inside. It's only the ones that are here within KT of energy. It's only the ones here within KT, an energy of KT. So that means that basically this Fermi sphere is still there, because the Fermi sphere is big in terms of KT, because it's equal to like 20,000 degrees. And so then that means that the sphere is still there, but the edges of the sphere get fuzzy, because that's where the electrons are jumping out. So basically, I get fuzzy edges, fuzzy edges. That's how you should visualize it in your mind, fuzzy edges. So as I turn on temperature, the edges, the Fermi sphere just sits there, but the edges get a little fuzzy, all right, because of this thermal excitation. But we want to, of course, make it more, quantitative than that. Okay, so I'm going a couple of minutes over, but I will finish in just a minute. So let's make this picture more quantitative. And to make it more quantitative, what we do is we can ask ourselves, what is the energy of all those electrons in the metal at some temperature T? So now let's get quantitative. And so we'll say, what's the electronic energy of all the electrons at some temperature T? And to do that, what I have to do is I have to add up, I have to sum, I have to look at the electron at every single mode, every single K. So that's the plane wave eigenstate K. I got to sum over every single K, and I got to sum up the energy of the electrons at every single K. And it's a vector, because it's a three-dimensional vector. And then but I got to know what's the occupancy of that mode? What's the occupancy of that mode at some temperature T? So there's some stat mech involved here. So this is the occupancy. So this is all the modes, but these are electronic modes now. These are the plane wave states, all the modes. This is the energy per mode. And this is the occupancy of each mode at temperature T. And so that is the energy at temperature T. But now to calculate that, and we're going to calculate it, to calculate that, we have to turn the sum into an integral. But to turn it into an integral, we're going to need to use that same concept, because we're going to use that concept we did before. We need the density of states. We're going to need to use the density of states. Oops, density of states, dE. All right, where this is 0 to EF, that's the density of states. Okay, so that's what we're going to do next. We'll talk about the density of states. And we also need to deal with this F of epsilon T, the occupancy. So these are the two things that we need to deal with, the density of states and the occupancy. Because what we're going to calculate in the end is we want to turn, this is the final thing, we want to know the energy of the electrons, which is equal to the integral from 0 to infinity epsilon times F of epsilon T, density of states, dE. That's the energy. That's the thing we want to understand. And we'll talk about that next time. Okay, bye-bye.
Thank you. Goodbye.
Thank you.
Thanks.
Bye-bye.